Vacuum energy is a ubiquitous background energy present across the entire cosmos. It is essentially the zero-point energy associated with the quantum vacuum. Various observable phenomena such as spontaneous emission, the Casimir effect, and the Lamb shift display effects of vacuum energy studies suggest that this energy influences cosmic actions on a grand scale. The highest value of the cosmological constant indicates that free space's vacuum energy is roughly 5 JeV per cubic meter or 10^9 joules. However, in line with quantum electrodynamics, the principles of Lorentz covariance and the Planck constant suggest an exponentially higher value of 10,113 joules per cubic meter. This discrepancy is briefly called vacuum catastrophe and is also known as the cosmological constant problem. Quantum field theory proposes that all core fields, like the electromagnetic field, should be quantized at every space point. In physics, a field represents a space filled with interconnected oscillating balls and springs, and the field strength is equated to a ball's displacement from its rest position as per this theory. Even the vacuum possesses a highly intricate structure in all computations of quantum field. Theory should be based on this vacuum model. The theory insinuates that vacuums implicitly possess properties identical to particles, such as spin, polarization, in case of light, energy, and so forth. However, most of these properties average out, leaving the vacuum essentially empty. A crucial exception is the vacuum energy or the vacuum expectation value of energy, which is the lowermost or zero-point energy of a simple harmonic oscillator that needs to be quantized. Lastly, vacuum energy can be visualized in terms of virtual particles or vacuum fluctuations, which are brought into and removed out of existence by the vacuum. These virtual particles and antiparticles usually annihilate each other shortly after being formed, but before that, they might interact with other particles or antiparticles, a phenomenon that can be illustrated using Feynman diagrams. In the field of physics, the concept of vacuum energy carries significant implications and prompts many intriguing scientific questions. Dutch physicists Hendrik B.G. Casimir and Dirk Polder first explored the idea in 1948, suggesting the presence of an elusive attractive force amid closely positioned metal plates. This Casimir effect, as it is now known, is attributed to fluctuations in vacuum energy. Although alternate theories have been proposed, the Casimir effect has been repeatedly verified, lending credibility to the existence of vacuum energy on a par with recognizable objects like electrons and magnetic fields. Among the more controversial projections is the creation of particle-antiparticle pairs, or vacuum fluctuations. Renowned physicist Stephen Hawking proposed that these fluctuations around a black hole's event horizon could theoretically lead to a black hole's gradual evaporation. The hypothetical scenario envisages one particle of the pair being sucked into the black hole, transforming the other into a real particle and radiating energy and mass into space. This energy loss is cumulative and hypothetically might result in a black hole's disappearance over vast timescales, longer for larger black holes. Moreover, vacuum energy could profoundly impact our understanding of cosmology. The principles of general relativity equate energy with mass, implying that a detectable vacuum energy could exert gravitational forces, potentially contributing to the cosmological constant and thus influencing the expansion of the universe. Speculation about vacuum energy also extends into the territory of free energy machines, devices exploiting broken symmetry in quantum electrodynamics to bypass energy conservation laws. Such machines remain conjectural, mainly as the full nature of vacuum energy continues to puzzle scientists. An innovative theoretical study proposed using the vacuum energy's field strength as an indicator of spacetime's resistance to localized curvature, potentially challenging traditional gravitational concepts. The unique approach suggested that the gravitational constant EGAEU might not be constant at all, but could depend on vacuum energy's field strength. Extensive experiments have been conducted to clarify G's value through precise measurements, but inconsistencies in the results have obstructed the achievement of a definitive conclusion. In the early 20th century, scientists like Georges Lemaître and Evgeny Lifshitz began to zero in on the concept of vacuum energy. Lemaître's perfect fluid equation in 1934 and the Casimir effect in 1948 both contributed to this understanding, although Lifshitz posited a different source for the Casimir effect in 1955. The discovery of broken symmetry and parity violation by Li and Yang in 1957, which earned them the Nobel prize raised further discussion around vacuum energy. Edward Tryon proposed the intriguing idea of a zero-energy universe in 1973, suggesting our universe might be a large-scale quantum vacuum fluctuation with balanced positive and negative energies. Despite efforts in the 1980s to identify the specific fields generating vacuum energy, their exact nature remains a mystery. Science fiction has had a field day with these theories, employing them in fantastic scenarios. Arthur C. Clarke's novel, The Songs of Distant Earth, features a starship propelled by a quantum drive. The Stargate franchise introduces a power source that draws zero-point energy from a mini-parallel universe Star Trek. Deep Space Nine presents an energy-draining weapon that uses vacuum energy. The popular video game Half-Life 2 takes this idea even further with a device known as the gravity guns that manipulates the zero-point field energy. The continuous exploration of vacuum energy sparks not only scientific curiosity, but also the imaginations of creators in various fields. Despite considerable progress, the true nature of the entities generating vacuum energy still remains one of science's great unsolved mysteries.